Okay, we're going to be talking about Sir Rutherford and his gold foil experiment to explain the structure of the atom. Up until now, we have learned that there is a negative charge particle called an electron, and from Rutherford's experiment, what they thought was that the whole atom was basically negative, and that inside that negativeness were those what he called corpuscles of negative charge particles, which we call electrons. And that was incorrect due to Rutherford's experiment. So his experiment, what he what he did was he took a lead box, and in that lead box he drilled a hole, and in that hole he put a material that basically decayed, broke up, and when it broke up, it one of the components of the breakup was an alpha particle, which is a very small particle, smaller than the atom. It's actually the nucleus of a helium atom, and and then what he did was that. So basically, what he created was a gun, and then what he did is he pointed that gun at a gold, what they call gold leaf, and the reason why he used gold was you can pound gold into a very, very, very thin layer to the point of it being as close at that time to a material that was one atom thick. It is definitely not one atom thick. It's thousands and thousands of atoms thick, but it was the closest way he could get to a substance that was one atom thick. And what he did is he put that gold leaf into a material. Okay, this is a better way of looking at it. He put it into a cage of a material that when the alpha particles hit it, the cage, it was actually basically think of it as a put the gold leaf inside of a basketball, and the inside of the basketball is coated with this material that when the alpha particle hit this material, it would shine a green glow. And he created a coordinate system so he could track where these alpha particles would go. Um, he thought his theory was that the alpha particles simply would go right through, and they wouldn't deflect at all. Um, so here are actually one of his results, and the angle of deflection is the angle off of if the particle went straight through. So if you drew a line from where the particle came out of the lead box, the reason why he used lead is because lead absorbs alpha particles. So therefore, the only particles that could have came out of the hole were going in a straight line. And that straight line basically went right into slash through the gold foil, and if it's zero deflection, it would have those particles would simply go straight through in a line and hit the backstop, the material that will glow green, um, basically in a straight line, and that is zero deflection. If the particle goes through the gold leaf and basically goes like it doesn't do this, but if it would straight through and took a right hand turn and went right up the gold leaf, that would be 90 degrees. If the particle basically hit the gold leaf and bounce directly back, that of course would be 180. So therefore, any angle of deflection greater than 90 means that that particle basically bounced off of the gold leaf and bounced back. So greater than, he used greater than 105-degree angle means it bounced back. So, so what happened was he did this experiment. Now, here are the results. And those are the actual numbers. So you see from the numbers that he counted 9 million times. So of course he didn't count. He had a bunch of graduate students. He's a sir, which means he's knighted in England, and he's a professor at, I'm not quite sure, Cambridge or Oxford or one of those colleges. So he has his grad students do this, and they actually record all the hits. And it takes, of course, days and days and days to do this. So what he found was, if you look, that if you guesstimate 9 million hits, 8 million of them either have a 0 deflection or a 5% deflection, and he felt between 0 and 5% it was basically the same, which means it went straight through. So 8 out of 9 times the alpha particles went straight through the gold leaf, i.e. the atom, which would indicate to him that that the atom is mostly empty space, since it didn't deflect or anything like that. So if it went straight through, it was going to an empty space. Then if you look at the bottom, what he says is that there were some that actually bounced back, meaning it hit something, so it hit something, so it would have to go backwards. So that changed his first result, which is that the atom was basically only empty space, because it actually hit something. Hitting mean it got close to something. Due to the Coulombic force, it would never actually hit it. It would just simply bounce back due to Coulombic force. And what he found is that thing must be, since it only hit like 100 out of 9 million times, it must be extremely small volume thing. Okay? And it must be extremely massive thing. So therefore, it was massive, because if it wasn't, it was about the same mass of the particle, then it would be like a billiard ball, and the alpha particle would hit it and it would go away, and it didn't. The alpha particle bounced back. Therefore, that substance, whatever it hit, is massive. And again, that caused his first result, 8 out of 9 times it went straight through, that atom is not all empty space, is actually something in it that is a very small volume. And then the degree angles between the 10 to 75, those deflections were explained that since the alpha particle is positive, what's happening is, as it's going by this thing that's massive in small volume, it's interacting with it, and it's basically being pushed away from it. And the only thing that would push away from a positive thing is another positive thing. So therefore, the deflections in between indicates that this thing, this area in the atom, is positively charged. So from his results, what we have is that going straight through 8 and 9 times indicates that the thing that's inside it is very small volume compared to the volume of the atom. It's actually 1/10,000th of the volume, meaning what that, and we'll get to that in a second. The bouncing back indicates that the thing that small volume sub area is actually highly massive. Actually, basically all the mass of the atom is in there, and then the angles of deflection in between indicate the fact that it's positively charged. And we call that, or he called that, the nucleus. That's what the nucleus means. So therefore, that is how we deal with how we explain the structure of the atom. So what from Rutherford's experiment, we have this small, extremely small volume, highly massive, positively charged area, which we call the nucleus, and it's approximately, the volume is approximately 1/10,000th the volume of the atom, which would basically mean take a golf ball or something the size of a golf ball and put it on the 50-yard line of Gillette Stadium, and the volume of Gillette Stadium would be the volume of the atom, and the volume of the nucleus would be the volume of the golf ball, approximately. Okay. His experiment really didn't explain anything about where the electrons were located, except the fact that he knew that the electrons weren't located in the nucleus because the nucleus is positively charged. So what he hypothesized, okay, so here are his results, and I explained them before. What he postulated about the electrons were that the electrons were located outside the nucleus, and they were in this region outside the nucleus, and they revolved around the nucleus like planets around the sun. And that's the problem, or that's the incorrect part of his explanation about the structure of the atom, because and it's called Rutherford's shortcoming. It's wrong because the electrons would be moving around the nucleus in a specific pathway, like planets around the sun. And since the nucleus is positive and the electrons are negative, that sets up an issue. Because if that was the case, then if the atom wasn't constantly adding, if the atom wasn't constantly getting in energy, then that electron would start being attracted to the nucleus, and therefore it would start spiraling into the nucleus. And as it spirals into the nucleus, technically it could be any distance away from the nucleus you could find the electron. Or the other way of looking at it is, if the electrons did revolve around the nucleus like planets around the sun, then the atom must be constantly adding or obtaining energy from its surroundings to keep those electrons away, because the Coulombic force needs to have a counterbalance. The Coulombic force is pushing the electron into the nucleus, and you need energy to keep it at its pathway outside the electron. The problem with this is that we know, or they knew, that the the atom didn't continuously add or gain energy. That's not how energy and atoms relate to each other. So therefore, that is a problem. And the next person we'll look at, whose name is Niels Bohr, he actually helped to explain this. Of course, there were a lot of other people who were involved, but that's the next major guy we're going to deal with. So therefore, Rutherford's experiment showed the structure of the atom. From his gold leaf experiment, he found that there was a region in the atom that's extremely small, very massive, and positively charged, which we call the nucleus, and the electrons reside outside them. Thank you.